In this tutorial I'm going to teach you the core concepts of the DOTS components. Writing DOTS game code requires a different mindset than programming with mono behaviors. DOTS consists of three parts: the Entity Component System, or ECS for short, the job system, and the burst compiler. All of these components can also be used independently of each other. The biggest shift in programming provides ECS in that it restructures how your data is laid out. While programming with mono behaviors, you are attaching them directly to game objects, and they execute their code from there. They therefore hold both the data for the object and the behavior. In programming with ECS, this is different. ECS has three distinct parts to it. They are entities, components, and systems. An entity is similar to a game object, except that it comes with no extra data like position, rotation, scale, layer, or tag. All of this data in ECS is stored in components. These are attached to entities. But components don't contain any behavior themselves. In ECS, systems are responsible for that. They contain entity queries and are designed to operate on multiple entities. For example, a system might have an entity query that targets all entities that have a position and a rotation component. Its code will then act on all entities that fulfill these requirements. Now enough with the theory, let's get to a real example and create a system that rotates a cube. The first thing we'll need to do is to install the necessary packages. For this tutorial you only need the hybrid renderer package. If you want to use more DOTS packages, you can look at my other tutorial that focuses on all the different DOTS packages that are available. After all necessary packages are installed, we can set up our scene. I'm just going to create a cube and attach the convert to entity component to it. This is part of the hybrid ECS approach. We can create and author our content in the editor with normal game objects, and in play mode they are converted to more performant entities with all the properties converted to their respective ECS component counterparts. The other option is ECS Pure, where you have no game objects and create and modify them only from systems. While this is possible, currently it would be quite cumbersome. You can always mix and match game logic that was written with mono behaviors with code that uses ECS. I currently recommend using ECS and DOTS for your performance critical tasks in your game only. Now we'll create our first ECS component. Our component should store the speed at which the cube should rotate. There's actually a create option specifically for ECS components. I'm going to name it rotation speed. This will create one with all the boilerplate code already written for us. The important things here are the included namespaces, that this is a struct and not a class, and that it implements the iComponent data interface. In the component we are just going to add loads with the name rotation speed. One important detail here is that the components can only contain value types and not reference types. That we can also attach it to a game object in the editor, we also need to add the generate authoring component attribute to it. This will automatically generate a mono behavior out of our component with the ability to convert itself to an ECS component. Now if we attach the rotation speed script to our game object, we are actually attaching the automatically generated mono behavior. When we now press play, the entire game object gets converted into an entity including our own component. When we now look into the entity debugger, we can see our entity with the custom component. Now in order to rotate the cube we also need a system. Go to Create and select System. This will also generate all necessary boilerplate code for our system. The important parts here are that the required namespaces are included, the class inherits from system base and overrides the onUpdate method. The onUpdate method is similar to the update method in mono behaviors, in that it executes once per frame. We can run any code inside the onUpdate method, but in order for us to use the job system, we will need to write a job. The boilerplate actually already implements a job for us. The important thing here of a job is the entity query. This determines on what entities the job will execute on. The example job targets all entities with a translation component and a rotation component. The ref keyword means that we can write to the component in the job, and the in keyword means that we can only read from the component. Declaring components only as read-only is important because then the jobs can be scheduled more efficiently. Because we want to create a system that rotates entities, we'll need to modify this query. Components with write access must always stand before ones with only read access. Our component only needs to write to the rotation component and read from the rotation speed component. In a job's body, we then only modify the rotation. Now when we go back to Unity and press play, we can see our cube rotating. We can also duplicate our cube and see them all rotating because they all fulfill the entity query we defined in our system. We can also look at this in the entity debugger, see what entity queries are defined in the system and what entities fulfill these requirements. As the last step, we should also multiply the speed with delta time to make this code frame independent. Now you might think you can just multiply the speed with delta time in the job directly, but because the job is scheduled and runs on another thread, we don't have access to the Unity APIs. That's where we use captured variables. Local variables from outside the job can be captured and used inside the job. It is also important that only native containers and buildable types can be captured. Buildable types are these types. Native containers are something from Unity. They are wrappers for non-buildable types, so you can also use them in jobs. For this example, we only want to pass a float to the job, and because floats are buildable, we don't need to do extra work here. You can declare it from outside the job and assign the variable because this runs on the main thread. Then inside the job, we just multiply the speed with the delta time. And if we look in the editor again, we can see that it still works. Now the last component of Dots, which we haven't yet spoken about, is the burst compiler. We don't actually need to do anything for the burst compiler to do its magic here. If you look at the burst inspector, we can see the burst compiler has translated our job. The only thing we have to watch out for with the burst compiler is the restricted features we can use. But if you run into one of these restrictions, we'll get a nice error message in the console, and you can either restructure your job to fit these requirements or just disable burst on this specific job. I hope you now have a basic understanding of how all the Dots components work. Thanks for watching.